morning. Welcome to the morning session. Before we start, I just wanted to point out there is actually an afternoon session again this afternoon. So Professor Prakash will be giving a talk after lunch. The first talk this morning is by Luca Rondi from Trieste, and he will talk on stability for the dialect scattering problem and its applications to cloaking.
Thank you very much. I wish to thank the organizer for inviting me here and for giving me an opportunity to give this talk in this very nice room and very nice institute. So what I would like to talk about is a very classical obstacle scattering problem, and even if the focus is towards inverse scattering, clearly I just want to talk about direct scattering, and then I will try to show you how this might lead to some applications to cloaking. So I'm just starting with a very simple direct scattering problem, and I just want to focus on sound art scatterers. So the idea is the usual one. You have a scatterer here, which might consist of obstacles, which are objects like this, or screens, but is an object like this. And by a scatterer, I always mean a compact set whose exterior is connected. That's the important part. And then if you send a wave, I'm considering acoustic scattering, so and in the time harmonic case, so if you send an incident wave, in this case, for instance, a planar wave, this is characterized by a wave number k and direction of propagation, and its field is given by the usual formula here. Then when this meets the scatterer produces a perturbation, which is given through a scatter field, and the total field is simply the superposition of these two waves, and it satisfies the following exterior boundary value problem. So it satisfies the reduced wave equation, or Helmholtz equation, outside the scatterer. It's the sum, the total field is the sum of the two incident and scatter field. And then, of course, depending on the nature of the scatterer, it satisfies different boundary conditions. And I'm focusing here on the case of sound hard scatterer, so we have here a Neumann type boundary condition. Plus, of course, the usual radiation condition at infinity. What I'm interested into, of course, this problem, everybody knows that it has a solution, a unique solution, provided K is reasonably smooth, and so this problem is very well known. What is maybe not that known is the stability of this problem with respect to scattering, which is clearly a preliminary part with respect to inverse scattering. So I'm not talking about inverse scattering, but I'm talking about stability of a solution with respect to variation on the scatter. So I'm formulating the problem in the following sense. So if you take a sequence of scatterers and the Kn and the corresponding solution, and you take a scatter and its corresponding solution, the question is simply the following: what happens if Kn converges to K in some sense? Does this mean that UN, the solutions are converging in some other sense? And here I just want to take the convergence in the minimal possible sense. So I'm just taking Kn converging to K with respect to the Hausdorff distance, and UN converging to U strongly in L2. And clearly these two guys live in different spaces, but this will be throughout the talk. Whenever a function is not defined, for instance, in the scatterer, it's always extended to 0 inside the scatterer. This happens to UN and to U, so they are all defined everywhere, just by this simple method. And of course, this question is trivial if you have enough regularity, but if you allow Kn to be almost anything, this is not trivial at all, because it's well known that even for uniformly elliptic problems, if you do the problem for the Neumann case, and the stability with respect to variation of a domain is simply not true. And there are examples, like for instance the famous Neumann sieve, which has been studied in the, I don't know, 20 or maybe more years ago by Murat and collaborators. And so this is not a completely trivial question if you allow Kn to be very wild. But it's a very important question. And the basic ingredient to that, which is the ingredient that actually is equivalent to stability with respect to variation of a domain in the uniformly elliptic case, is the so-called Moscow convergence. So I want to spend a few words. It looks very complicated, but it's really not. I would like to spend a few words on that. So let's consider these Sobolev spaces. An is the H1 of Br plus 1 minus Kn, and A is the same thing with K. And I think this to be subspaces of L2 into values into Rn plus 1 in this very easy sense. If you take V in this space, you identify it with V and grad V, and you extend V and grad V to 0 inside K. And so in this way, these are all subspaces of L2, and so Moscow convergence is a convergence of subspaces, and you can define it in the following way. So you have two parts. The first part is a kind of weak closure, in the sense that if you take a subsequence belonging to A and K, which converges weakly to an element in L2 and to values in Rn plus 1, then these elements needs to belong to A. And this is a kind of, and you have weak convergence in L2. So this is a kind of weak closure up to subsequences. But you have another property here, which says something more, that if you start from an element of A, you can strongly approximate it by elements coming from An. So you have a sequence belonging to An such that you have a strong approximation in L2. And so this is the kind of structure you have. And as again, so what does it mean that VV belongs to A? V means that V and capital V are 0 in K, and the outside is the distributional gradient. So this is the key property for uniformly elliptic equations. And so it has been extensively studied in the late 90s and beyond. And so I just mention a few results in this direction. So you assume that Kn converges to K in the Elsdorf distance, and then you would like to find condition for Moscow convergence. So in dimension 2, the situation is pretty well understood, and there is this result by Bukur and Varchon that says the following. So the key point in dimension 2 is that the number of kinetic components is bounded. And if this is not, the Neumann sieve examples gives you a counterexample to that. So this is an essential part, but this is almost a necessary condition. Then you have convergence in the sense of Moscow if and only if you have a convergence in measure. And since this is a necessary condition, this result is almost it's almost optimal, I would say. And a starting point from this, and actually a very interesting sufficient condition, was given a few years earlier by Chambol and Doveri, and with again the number of kinetic components of a boundary here, but is almost the same, is bounded, and the measure of the boundary is uniformly bounded. Then you have convergence in the sense of Moscow. In dimension 2, the situation is slightly easier, because essentially you use duality and you transform it in the Neumann problem into a Dirichlet one, and so it's much easier. In dimension 3 and higher, you cannot do that. Yeah, sure.
Kn minus K measure goes to 0?
No, the measure of Kn goes to the measure of K.
Oh.
Okay, so it's this is the yeah, because you know out of distance you can have a measure zero set which is going to the full set. You can approximate in the out of distance the whole domain with measure zero set. We just take enough dense points. So you need to have this kind of course, you cannot do that with if a number of connected components of K is bounded, but
I don't know. If only their measures go to each other, it sounds like they could be just about anything.
But you've got K and K and Hausdorff.
Yeah. This is the basic,
sorry.
starting point. Sorry. Okay. In dimension 3, so the situation is more complicated, and so you need some regularity assumption. You don't have any regularity here. And in dimension 3 you need something of this kind, and usually this is a kind of Lipschitz type regularity assumption, and there has been a result by Giacomini and one by myself and Menegatti, which are pretty much similar, where Giacomini result is slightly more general in one sense, ours is more general in another sense, but more or less the kind of Lipschitz condition is the same one. Okay. And so using this, you can prove a stability result for also for our exterior boundary value problem for the Helmholtz equation, and this has been done with Menegatti. And so the hypotheses are the following. You have convergence in the out of distance. You need the convergence in the sense of Moscow, which is a key ingredient. Plus, since we are dealing with the Helmholtz equation, you need we need a uniform Sobolev inequality of the following kind, and then you have the convergence as required in this way. And this is pretty useful as a preliminary result for studying also the inverse problem, because it gives you uniform estimates. For instance, uniform decay estimates for scatter fields for class of large classes of admissible scatterers. So you have kind of a priori estimates using these kind of results. But I don't want to deal much more with that. What I would like to go is to show a little bit how these kind of results may lead to cloaking. So this is the intermediate step. I want to do an approximation of screens in two ways, by thin obstacle and then by lossy layer, and I'm going to explain immediately what this means. So, so I'm taking a screen, or better a scatter formed by a finite number of Lipschitz, or screen with some kind of Lipschitz condition, and I want to make an approximation using essentially the result before. So the first step is to show that there exists a kind of regularized distance, this d tilde, which is a Lipschitz function, which is controlled by the distance from k below and above, and that satisfies the following condition. If you take an epsilon neighborhood in this of k in this regularized distance, then for epsilon small enough, you have that this k epsilon is still is a scatter. It's still a scatter. Actually, it's an obstacle because this is the closure of an open set, and Rn minus k epsilon is connected. And so you have this condition. Plus, you can prove, if you have this Lipschitz condition, that you have a uniform Sobolev inequality. And this leads you to the following result about saying the following. So you can approximate a screen by using thin obstacle in the following way. So you take, as before, a scatter formed by Lipschitz screen, and then you take a sequence of Kn, which are simply k epsilon n, where k epsilon n is a sequence going to 0. And then you immediately have the following three conditions. So convergence in the out of distance is trivial. Actually, convergence in the sense of Moscow is easy in this case. And uniform Sobolev inequality we had from the result before, so you are able to prove that you have a convergence of solution. So what you are doing here, you are approximating a screen by a thin obstacle surrounding it. Why this is useful and towards cloaking? Well, this is the main idea. So you have a screen which is an n-1 dimensional set. Everything I'm talking about works in any dimension, 2 and higher. So you take a screen which is an object like that, and what you do, well, you say that this k epsilon, which is a thin obstacle surrounding it, is a good approximation for the direct problem for sound hard scatters. And of course, when you do this, you take this k epsilon, you take this as a whole thin obstacle. But of course, since this is an impenetrable obstacle, you can think that you obtain the same result by taking a hole in here. So you have the same result if you take a hollow thin obstacle, and you can approximate that. And clearly, if you think what in this hole, which is this lighter color region, you could put anything, and that would be perfectly cloaked. Okay, this is clearly cheating a little bit, but this is the main idea. The main idea is the following. Okay, instead of having here a sound hard hollow obstacle, I would like to replace it with a medium that does the same kind of approximation, that at the limit goes to the behavior of a sound hard screen. And in this way, with this, if I can put such a medium in here, I might be able to at least approximately cloak what is in this hole. And this is what I'm going to do. This is the plan. Then I will going to explain how then this is related really to cloaking. But this is the intermediate step. So I want to replace the obstacle with some kind of non-homogeneous medium, and so I'm going to do the following intermediate step. So you take a sequence of numbers, positive numbers going to 0, and you take Kn is okay. So Kn is K epsilon n. Hn is the light part, and then I will use also Jn, which is something in between. Okay, it's K3 epsilon n over 4. Okay, so it's one set in between. So A is the usual subspace of L2, which is H1 Br plus 1 minus K. And then instead of working with Sobolev spaces like this as before, I replace it with a weighted Sobolev space on this set with a suitable weight sigma n, which is related to the coefficient epsilon n. And of course, I need to choose carefully the coefficient, and the coefficient, the assumption of sigma epsilon is the following. Outside k epsilon, this is simply the identity, no problem. In the thin layer, k epsilon minus k epsilon half, I'm just, okay, for simplicity here, I'm taking sigma epsilon to be a scalar, and I'm just assuming this asymptotic behavior for some constant lambda. Okay, then from this, I have a Moscow type convergence. In the sense that, as you can see, this is pretty much the same as before. So we have a weak closure up to subsequences for any v and v in this space. If you can find a sequence uk in this set such that, okay, you have such that these elements converges weakly to this, then these belong to A. And here you can note the weight coming up here, just multiplying the gradient. Okay, there is also this other part, but it's less important. Want to point out the weight here. Moreover, you have a strong approximation for any element in A, provided U is bounded, you can find a element in H1 Br plus 1, satisfying the following. Un is 0 in Jn, so in particular in the cloak region you have that this Un is completely 0, and you have a strong approximation in L2, again with this kind of weight in here. And of course the usual thing, whenever something is not defined in some region, is put to 0 there. So this is a kind of convergence. So you have really the same kind of Moscow type convergence, only in this weighted setting. And so the idea is the following. You would like to approximate a Saunders screen by using a suitable medium in this thin layer. And as what concerns the sigma weight, you have you think this is a cross section. So you have that these objects, this is a thin layer. This is going to be thinner and thinner, closer and closer to the screen, and the coefficient is going to be lower and lower. And the idea is to replace the Laplacian term with this elliptic equation with coefficient sigma epsilon. And this essentially would be enough if you are dealing with uniform elliptic equations, but here we are working with Helmholtz equation, and we need to deal also with a lower order term. And so we need to do something to modify also k square of u. And the idea is to modify it by inserting here another coefficient, q epsilon, and this q epsilon represents a highly absorbing medium in this thin layer. So namely, the conditions are the following. So you replace your Helmholtz equation with this equation representing a non-homogeneous medium, and you have the following assumption. Sigma epsilon and q epsilon are simply identity and 1 outside k epsilon. So outside k epsilon you have exactly the Helmholtz equation. In the thin lossy layer you have the same condition of sigma epsilon. And then why this I'm calling lossy layer? Because the main assumption is that the imaginary part of q epsilon is going to plus infinity. And the real part is of essentially the same order, but they need not to go to infinity too fast, because you need this to go to 0. So this is clearly the measure is going to 0, so q epsilon can be large but not too large. And the most important thing is that in k epsilon half, which is essentially what I call the cloak region, you have no whatsoever assumption on sigma epsilon and q epsilon. And then what you can do is the following. You can take an incident field, solve the problem, the usual scattering problem with this non-homogeneous medium, as usual. And then what happens is, as epsilon goes to 0, no matter what you have in the cloak region, this function, which is put to 0 in k epsilon half, converges to you strongly to the solution to the problem where k is a Saunders scatterer. So you have exactly the same kind of approximation. Instead than with a thin obstacle, you use this kind of inhomogeneous medium, and you can allow these whatever it is in the cloak region k epsilon half. Okay, so this is the result, which I obtained with Jingxi Li, Ongyu Liu, and Gunther Ullmann, who unfortunately is not here. He should have been here. But and so the following is, and the result is the following. So I recall that the Sommerfeld radiation condition implies that the scatter wave is characterized by its far field pattern. And then the idea is the following. The approximation goes this way, that u epsilon, this you can think as the near field error, and you can think this as the far field error. So the near field error and far field error goes to 0 with uniformly with respect to what is inside the cloak region and of the direction of propagation d. And this is the kind of result. Unfortunately, this is, for the time being, only a qualitative result. We are planning to try to prove some estimates and to give an expression to this omega, but up to now we only know that this is going to 0 uniformly. But the important thing is that this is uniform with respect to these two coefficients in k epsilon half. Okay. Of course, you can think, okay, this is kind of cloaking, but this region is not very nice because as epsilon is going to 0, this region is getting thinner and thinner, and so you don't really get into, I mean, it's not very useful. And so to go really to full and partial approximate cloaking, the key point is going to be the previous approximation of screens, but I also need to use transformation optics. So and now I'm going really towards cloaking, and so I'll start with classical results. So cloaking has been attracted a lot of attention recently. Actually goes back more than 10 years ago by this paper by Greenleaf, Lassas, and Ullman. But then, okay, in recent years there have been contributions by thousands of people. So apart from those three, Kurilev and Vogelius, Bob Kohn, Nguyen, and I don't know, many others. I hope not to forget anybody who is in the audience studies that. But there has been really an explosion of interest and of number of papers in this area. But let's go back to the original idea and let's try to explain that. So take take now a k, which is simply a point. Everything I said before worked also in that case. So also not only for k a screen, but for k simply a point. So you need to keep in mind that. So the idea is the following. I want to cloak something which is in this region D, and I want to cloak it by putting some suitable medium in this annulus omega minus t. And the idea is the following. I look at a virtual space in which there is only this k, and I transform this virtual space by a function f, which is bijective from Rn minus k to Rn minus t, and which is the identity outside omega, and which is some transformation which maps omega minus k into the annulus. And then what happens? In the virtual space, you are solving the usual Helmholtz equation outside k. In the real space, when you do the transformation optics, you are solving this kind of equation, where the coefficients are given by the pullback of sigma and q, where sigma and q are this one in this case, and the solution is simply the transformation of the solution to the previous problem. And this is the rules how this coefficient goes. And then what happens is the following. If you do a scattering problem with respect to this is invisible. So you don't really see anything. And this is telling you that if you send an incident field, then u is equal to ui in Rn minus omega, because the scatter wave simply is 0. But since u and u tilde are equal outside omega, because the transformation is the identity there, this means that you cannot really see anything from outside what is inside omega minus t. And so this cloaking medium, which you put there, is a perfect cloak. The problem is that this f1 is not by Lipschitz, and so this cloaking medium is singular. So it's something that you cannot really do in practice. So what we try to do is to do an approximate cloaking, so to build some medium that effectively cloaks up to a certain extent, but is feasible from a practical point of view. And the idea is simply the following. So what you do, you take k. Now the region you want to cloak is d1/2, and the cloaking medium is going to be in omega minus t. And then this is in the real space, and then you look at the virtual space. In the virtual space, we know how to approximate this sound hard object by a thin lossy layer. And this is what we are going to do. So we are putting our thin lossy layer around here in this thin layer, and we know what you can cloak, what is inside this k epsilon half. And so we know how to cloak in the virtual space, and we need to go back to the real space. And this we are going to do by this by a transformation, which is bijective for Rn minus k into Rn minus k, and which is depending on epsilon, because now there is an epsilon here. This function is the identity outside omega, and then you have a transformation inside these other objects. Okay? And this is for the full cloak, but we can also do partial cloak. I will explain why I'm calling this partial cloak, just by replacing the point by a screen. In this case, for instance, a screen is simply a part of a plane, of a hyperplane, actually. And you can do the same kind of consideration. So this is k epsilon. So you have the same geometry. Okay, and actually, together with Lidiu and Ullman, we explicitly described in many situations these kind of functions. So these functions here, which are explicitly described, you can really write them down and understand what's happening. So the idea is, okay, let's try to see what happens if, so we know what happens in the virtual space if we put the right kind of lossy layer in here, and let's try what this means if we transfer this situation by these transformation optics into the real space. And this is what we are going to do. So this is sigma epsilon and q epsilon are exactly the same coefficients that I used before in the in the virtual space. Okay, this is the thin is represent its. So I'm going back. So this is going to be the Helmholtz equation outside k epsilon. You have a thin lossy layer in this here, and you have no information whatsoever what's in this lighter region. And then you simply go use the pullback, and instead of using the solution u epsilon, you consider its transformation u epsilon tilde, and you get this pullback operator. And then in the real space, you have the following scattering problem. You have this non-homogeneous Helmholtz equation, and you have usual incident wave plus scatter wave, and you have the usual Sommerfeld radiation condition. But the important thing is, okay, u epsilon and u epsilon tilde are actually equal outside omega. So, for instance, they have the same far field. So their behavior at infinity is exactly the same. So u epsilon infinity is equal to u tilde epsilon infinity, or vice versa. It would be more interesting. And so this is it. But we know how to study and characterize these elements. And so we can finally prove the following result. So if you take so a point, what happens? So if you take any direction of propagation, what we have is that u infinity is identically equal to 0, because in the virtual space, you are simply, what happens in the virtual space is that you are solving the Helmholtz, the scattering problem with simply a point sound as scatter, which is completely invisible. So you have that for whatever it is, this is u infinity. And then this is the theorem what you can get is the following. You have u epsilon infinity tilde. What is this? Okay, I have observed before, but this is actually equal to u epsilon infinity. Okay, but our previous theorem says that u epsilon infinity minus u infinity is bounded by this function going to 0. Okay, and since this is this is 0, you have exactly this. And this is, since we have no assumption whatsoever on let's let me go back one. On these coefficients in k epsilon half, we don't have any assumption whatsoever on the coefficients sigma epsilon tilde and q epsilon tilde in the cloak region. So now you have a very big cloak region, d1 half, which is a very big portion of space. You can put whatever medium in there, no matter what, and from the outside measurement, and if you put into omega minus d1 half the cloaking medium that you get from this transformation, what you can see from outside is something which is of the order of omega epsilon. So if this is below your noise error, then you cannot see really anything. And so this is approximately cloak from every direction. And I have added here a remark. Actually, you can allow in this cloak region, you can allow the presence of scatterers, sound soft, sound hard, and also impedance scatterers. And under certain conditions, you can also add sources. So you can effectively cloak also some active medium. There might be some activity inside, but under certain conditions, you can cloak also that with the same construction, with the same cloaking medium. And so this is rather interesting. This is the full cloak. Full cloak means that this goes for any direction of propagation, but this is not always the case, that you can really observe things from any direction. Most applications, maybe, or in most situations when you would like to cloak, you can assume that people are looking at you or probing you from certain directions. So you can think of radar. It's difficult that you can go up to the plane and try to understand what the plane is. You probably are just using some directions. And this is why you can do that, and you can use approximate partial cloak in the following sense. So if you take, instead of a point, you take the screen as before, which is a part of a hyperplane, and you do the same kind of consideration, then what happens, okay, if you take some direction of propagation, it's clear that this is not invisible to any direction. It's invisible only if you take a direction of propagation of a planar wave which lies in this hyperplane. Then this is invisible, you don't see it, but otherwise you can see it. But in any case, if the angle between the incident wave and the perpendicular to this plane is small enough, then what you can see at infinity, the perturbation is of the order of this angle, essentially. So it's very small if the angle is very small. And then what you can do, you do the same thing. So if you are assuming that you can be probed only from these kind of directions, which is a reasonable assumption, and so if this is bounded by tau, then what you can say is that if you tilde infinity epsilon, well, this is equal to u in the virtual space, but in the virtual space, this is bounded by that. Okay, you can add and subtract u infinity, so you know how to control this. This is of the order of omega epsilon, and you know how to control this because this is of the order of tau. So if you are pretty sure that this tau is not big enough, and then you can have an approximate cloak and a partial cloak only for certain directions. Not any direction, but maybe this is just what you might be interested into it. And again, this is fully independent of what happens in the cloak region, whatever medium it is, and again, you can put scatterings in it, and you have the same condition that allows you to put sources, which means in order to put sources, you need to have that the medium in the cloak region is slightly absorbing, and you need to have a relationship between the absorption and the intensity of the sources. Okay, you need to have something like that, but you can allow some active content going on, some active thing. And so this is what I wanted to say, and I thank you for your attention.
Any questions?
At the beginning, you said that something about Neumann sieve.
Yes.
I don't think it's correct example because Neumann sieve is kind of singular perturbation, right?
Yes, but you can think you have many screens, approximately a Neumann sieve. So it's not clear that the stability is.
I mean, we cannot consider it as counterexample to stability because Neumann sieve is very singular perturbation of the domain, right?
Yes, but it tells you that unless you put some condition on your scatterer, for instance, finite number of kinetic components or something, you don't have stability for the standard scattering problem for obstacle. Of course, it's a singular situation, is a pathological situation, and mostly may not be encountered, but. Unless you put some condition, you don't have any stability. And so, for instance, you don't have uniform a priori estimates if you don't put a few conditions there. If you allow just K to be anything, well, this is not going to be, it's not going to work. If you say, okay, I want to find any possible scatterer, well, that's not going to work. Of course, it's you need to go to very strange and very difficult objects not to have stability, but this is the case.
So your regularity assumption is basically in the Sobolev embedding condition that you put up, is it?
Yes.
That's what.
Yes.
So you said for uniform Lipschitz that implies that.
No, the Moscow convergence implies stability for the Neumann problem. It's if you take Laplacian u minus u instead of plus u, and you take that problem, Moscow convergence and convergence of the Neumann problem for that equation is exactly the same, is perfectly equivalent. But now I need the Sobolev embedding because I'm using the, I don't have a right sign in front of you. I have a Helmholtz equation, and so I need some extra thing there. But the key is the really, I mean, it's the Moscow convergence. It's tell you when these elliptic problems are stable, these Neumann elliptic problems are stable with respect to variations of the domain. The key point is the Moscow convergence. Because it's natural. I mean, it's test function spaces, and you need to control how these changes. It's the space of solution. You need to control how it changes along the sequence.